Hello again. We are here with our last video for this worksheet for section 2.8. We're going to work through number 1. We will consider a globe. We would like to find the surface area. So the formula for surface area of a globe is 4 pi r squared. We're going to do this by measuring the circumference because that's just what's easier to do in real life. So first we're going to find a formula for the surface area of the globe in terms of the circumference. So we want area to be a function of the circumference, and we can do this because right now we have them both written in terms of r. So if we take the circumference formula and we solve for r, it's going to be equal to c over 2 pi, and then we will substitute in here. So we get a is equal to 4 pi times c over 2 pi, that whole quantity squared. And if we simplify this, we will get c squared over pi. Okay, so there's our formula for the surface area of the globe in terms of the circumference. Let me write that over here so it's easier to see. Next, we're going to find dA in terms of DC and C, and the way that we are going to do this is simply by differentiating. Okay, so we are going to differentiate A. We're going to differentiate A, and we are going to differentiate c squared over pi. So the derivative of A, we're just going to write as dA, and the derivative of c, and we're doing this with respect to the variables that are on each side. So we will have 2c over pi. But this is basically like implicit differentiation, so we need to multiply by the derivative of c then. So that will be a dc. Now another way to think of it, if we are differentiating, see, here's the thing, we don't really have what we're differentiating with respect to. So let me just write it back like this, c squared over pi. So we're going to be differentiating that. 1 over pi is a constant, so we can pull that out of the derivative, and then we end up evaluating c squared. So 1 over pi, power rule for c squared says we're going to have 2c, but c is varying, okay? Let's say we're differentiating with respect to r. c changes as a function of r, so does a. So then we would need to multiply by the derivative of what's inside, and what's inside is just c, so we'll have the c prime there. But instead of writing c prime, we are going to write dc. Okay, so this then gives us that dA, the differential for a, the little change in a is going to be 2 over pi c times dc. And here is our formula that involves our differentials. Now the way that we're going to use this is in part C. If we measure the circumference to be 20 inches, so we're measuring the circumference to be 20 inches. This means C is equal to 20. There's a possible error of plus or minus 5 inches. This means that C could be changing by positive or negative 5 inches. Essentially, we are saying DC is the magnitude of 5. We are going to find an estimate of the relative error. So the relative error in this case is given to us, but we could also go back up to our formula up here. The relative error is going to be approximated by dy. In this case, that's dc. And the approximate value is going to be the measured c value. I'm sorry, I used the wrong letter there, because a depends on c. So dA over a. Oops. Okay, so dA we can find by plugging in our c value into the formula that we got in part B. So 2 over pi times 20 times our dc value, which is going to be 5, and this will give us, let's see, 200 over 5. But then we also need to find what a is. Now a and c are related by our formula in part a. A is c squared over pi. Sorry, spaced out for a moment. That's going to be 20 squared over pi, or 400 over pi. And if we take these and plug into the relative error formula, that's going to be approximately dA over A. So that is 200 over, that needs to be a pi, over pi, divided by 400 over pi. So the pi's will cancel if we multiply by the reciprocal. The pi's will cancel, and we will be left with 200 over 400, or 1/2. So that's our relative error, and the percentage error, so let me write that here. Relative error, at least, is approximately equal to 1/2, and the percentage error then is going to be approximately equal to 1/2 times 100, or 50%, which honestly is a pretty terrible error. But if you think about the size of the values that are done here, if we have something that is measured as 20 inches and we have a possible error of 5 inches, that is very significant. And it becomes even more significant when we think about the fact that we are squaring that value to get our approximate A value. Okay? So this does wrap up our discussion of both linearizations and differentials in section 2.8.